Welcome back to our class notes on 8-17. When we last left off, we were taking a look at the 10 rules for determining oxidation numbers or oxidation states, and we're on rule number 5. Hydrogen, as we had said, always will have an oxidation number of +1 when it is with a more electronegative element, when there's an element stronger than it. Most of the nonmetals are stronger than hydrogen. So when hydrogen is with most nonmetals, it will be a +1. The ones that it won't be a +1 with necessarily are ones where hydrogen might be stronger. So these would be boron, silicon, arsenic, phosphorus, and tellurium. Hydrogen will always be a -1 oxidation number when it's with any metal. As we mentioned, hydrogen's oxidation number is 0 when it's with another hydrogen. And that's just a restatement of rule number 1. When an element is with itself, it has an oxidation number of 0. Rule number 6, the oxidation number of a neutral compound must always add up to 0. So the total oxidation number, and they're talking about the total number, adding up all the oxidation numbers of every atom in the compound. It must be 0. And this goes along with rule number 2, dealing with binary covalent compounds. Let's take a look how this works. Here we have methane gas, Ch4. In this compound, it's binary covalent. We have carbon, we have hydrogen, so we're going to assign an oxidation number to the more electronegative element first. Carbon's 2,5, hydrogen is 2,1. So carbon gets the oxidation number that it prefers, which is equal to the number of electrons it would need to be stable. Carbon's in family 4. It needs 4 electrons to get its total of 8 and satisfy the octet rule. So carbon's oxidation number here is -4. It's not 4 minus. 4 minus would mean that carbon went out and acquired 4 electrons by stealing them off other atoms. It's -4. So we go ahead and we assign carbon. It's -4. We only have 1 carbon here, so the total for carbon is -4. Rule number 6 tells us that the oxidation number of methane, this neutral compound here, must be 0. So that it must add up to 0. So if the total negative oxidation is 4, then that would mean the hydrogens would have to add up to 4, because -4 and 4 is 0. We have 4 hydrogens here. So the total positive is 4. We have 4 hydrogens. That means each hydrogen must be +1. +4 divided by 4 is +1. And that's great because we learned in Rule 5 that hydrogen is +1 when it's with a more electronegative element. And in this compound it is. On to rule number 6, or number 7. The sum of the oxidation numbers for a charged substance must equal the charge of this. So when we're dealing with polyatomic ions, the polyatomic ions we learned had charges. So the oxidation numbers, when we total the oxidation numbers of the atoms in a charged substance, they need to equal the charge of that substance. So let's take a look as an example at the phosphite ion, PO3 3-. Well, this compound has a full ionic charge of 3-. The oxidation numbers of the phosphorus and the oxygen in this compound must total -3, because the oxidation numbers must add up to the charge of this substance. So who do we assign first? Well, we look to see who has the higher electronegativity, oxygen or phosphorus. Oxygen is going to get its -2 almost every time if you look at Rule 4. Why is that? Because oxygen's 3.5, phosphorus is only 2.1. So that means the oxygens will get assigned a -2. So here's our phosphite ion down here, PO3 3-. The oxygens get their oxidation number of -2. We have 3 oxygens at -2, so the total minus is -6. The total minus is -6. The total of the oxidation numbers of phosphorus and the 3 oxygens must total -3. Why is that? Because the compound, this polyatomic ion, is 3-. So what would phosphorus have to be in order for it to add up to -3? Well, the phosphorus would have to be +3, because +3 minus 6 is -3. We only have one phosphorus here, so that means the phosphorus itself, this phosphorus atom, is +3. Rule number 8. The oxygen numbers can be assigned to both molecular and ionic compounds. That's no surprise. We just did that when we looked at number 6 and 7. It's just a general statement. It's really not a rule. Number 9, monoatomic ions. Their oxidation number must equal its charge. So Al3 plus, that's the aluminum ion. It would have an oxidation number of +3. S2- is the sulfide ion. It is fully charged 2-. It has ripped 2 electrons off something. So its oxidation number must be plus or -2. Its oxidation number must be -2. Rule number 10 and our final rule. The alkali metals will always be +1 oxidation number because they can only become 1+ in chemical reactions, and we're not talking about hydrogen here. We're talking about the rest of the alkali metals. And the alkaline earth metals will be +2s. Let's take a look at some example problems where we are going to assign oxidation numbers. And first we're going to take a look at potassium permanganate, which the formula is KMnO4. This one has ions in it. Potassium is always 1+. The permanganate ion, we remember, is 1-, but we're going to go ahead and assign oxidation numbers to each of the individuals in here. Once again, we know K will be 1+. Rule 10 tells us the alkali metals get their charge. Oxygen is going to be -2. Rule 4 would tell us oxygen needs 2. It's the strongest electronegativity in this entire compound, so it gets to be -2. So we come over here. The oxygens get their -2. The potassium gets their +1. The total oxidation numbers for KMnO4 must equal 0 because KMnO4 overall does not have a charge. So let's take a look. We've got 4 oxygens at -2. They add up to -8. We got 1 potassium at 1+. It adds up to +1. The overall charge or the overall oxidation numbers must total 0. So we have a +1 and a -2. What does that mean the manganese has to be? Well, if you think about it, it would have to be +7. +1 and +7 -8 is 0. So manganese would have to be +7 so that the total oxidation state or numbers of KMnO4 total 0. So manganese here would be +7. So the potassium's +1, the manganese is +7, and the oxygens are -2, and we are done with number 1. Example number 2, oxidation numbers for sulfur tetrafluoride, which is a molecular compound. Who do we assign first? The most electronegative element. Again, there is an electronegativity on the very back page of these notes if you need to take a look at an electronegativity table. We know fluoride gets its -1. It's the strongest of them all. It gets the -1. Rule 3 tells us that. So right away we can assign fluorides -1 or fluorines -1. We've got 4 fluorines at -1 for a total of -4. SF4 has no charge. It is not an ionic compound. So the oxidation numbers must total 0. So what would the sulfur have to be in order for the numbers to total 0? Well, the fluorines add up to -4. The sulfur would have to be +4. +4 -4 is 0. So sulfur's oxidation number or state is +4. Example number 3, Xenon Oxy Fluoride. The formula is XeOF4. And yes, we can assign it the oxidation numbers to noble gases. Any atom in a compound can have an oxidation number assigned to it. Here, how do we decide to go about assigning them? Well, our rules tell us that the most electronegative element gets its number first. Fluorine's a 4O, oxygen's a 3,5, so fluorine gets its -4 first. Oxygen gets its -2 second. We've got 4 fluorines at -1 for a total of -4. The oxidation numbers of all the atoms in this compound need to total 0 since this compound, this binary covalent compound, is not charged. We have 1 oxygen at -2, so it's -2. So we have a -2 and a -4. What would xenon need to be in order for our total to be 0? If you come up with 6 plus 6, you are correct, because +6 minus 2 minus 4 is 0. So xenon would end up +6. Let's take a look at another example. The perchlorate ion is ClO4-. Once again, we can assign oxidation numbers to anything. However, in this one, this does have an overall charge. So we have the Cl, we have an O4. Who gets assigned first? The O gets it first because it's 3.5. Chlorine is 3O, so it gets its number second. Oxygen prefers a -2. We have 4 oxygens at -2, so the total negative is -8. However, this compound does have an overall charge of 1-, so the oxidation numbers must add up to -1. So what would the chlorine have to be in order for this to occur? What would we add to -8 to end up with -1? If you said +7 is correct, you would have it. The chlorines have to be +7 because +7 minus 8 is -1. Overall, it's a 1-. That would be showing us that our numbers add up correct. So the oxygens are -2, the chlorine is a +7. Our next compound, P4O6, is tetraphosphorus hexoxide. How do we assign numbers here? Well, we have phosphorus and oxygen. Who do we assign first? We assign it to the more electronegative element first. Oxygen's a 3,5, phosphorus is only a 2,1, so oxygen gets its -2. So over here, we're going to go ahead and give oxygen its -2. We have 6 oxygens at -2, so the total minus is -12. P4O6 has no ionic charge, so the oxidation number would add up to 0, the same as the charge of the compound. So that means the phosphoruses would have to total +12. +12 and -12 adds up to 0. However, we have 4 phosphoruses here. We have 4 phosphoruses that add up to +12. That means each of the phosphoruses would be +3. So the phosphorus is +3. The oxygens are -2 each. Here's some quick examples. What's the oxidation number of As4? Well, this is element. This is elemental arsenic. Arsenic has only arsenics with it, so its oxidation is 0. We're just following rule number 1. What's the oxidation number of barium ion, Ba2+? Well, it has a full charge of 2+, so the oxidation number of a barium would have to be +2. How about the phosphide ion, P3-? Well, it has a charge of -3. It has a charge of 3-, so the oxidation number would be -3. Here we have elemental oxygen, O2. This is not the peroxide ion because there's no 2- there. This is just elemental oxygen. When an atom is in its elemental form, its oxidation number is 0. We have 2 more examples that we will be covering, and we will cover these on our next video. Once again, if you have any questions on any of this stuff as we go over it, do not hesitate to email me a question at any time that you need.